In this example, we have that a ferry in Burlington, Vermont often takes people across Lake Champlain to Plattsburgh, New York. The ferry travels at about 25 miles per hour north 30 degrees west from Burlington to Plattsburgh against a current in the lake that travels at about 5 miles per hour at a bearing of south 50 degrees west. We will find the true speed and bearing of this ferry, taking into account the intended direction as well as what the current does to this overall system. I am going to demonstrate how to do this problem in two different ways, as there are multiple methods to establish this. First, I'm going to go about this using the traditional techniques involving vectors. So, if I want to work with this traditionally with vectors, I'm going to take my information and try to make this into component form. If I draw a picture for this example, though, we have first that the ferry travels at about 25 miles per hour north 30 degrees west from Burlington to Plattsburgh. So that means I'll draw a little coordinate plane to represent where I'm starting and to demonstrate the bearing here of north 30 degrees west. That means if we face north and turn 30 degrees towards west, that direction is the direction of the ferry here. We have that this is going against a current in the lake that travels at about 5 miles per hour at a bearing of south 50 degrees west. So if I draw that from this same position, I can draw this as south 50 degrees west. I have the current vector. Note that I'm going to draw the current vector much shorter. The reason for that is because in terms of magnitude, I can say the magnitude of the ferry vector has a magnitude of 25 miles per hour, whereas the current vector only has a magnitude of 5 miles per hour. The combination of the intended direction of the ferry as well as the current will help us find what the true resultant speed and bearing of the ferry is. In this case, I'm already expecting my vector to still be a vector that, when drawn in standard position, would end in quadrant 2, as the current should not be enough to overtake the overall direction of the ferry. So I expect my addition of these two vectors to be a new vector that extends out from in between these two. But how to find that? That is our question. Our goal here is to add our two vectors. F is what I'll call this, and we're going to add that to the vector C for current. So those are the variables I'll use here, F and C. But we need to figure out what F and C are in component form. Keep in mind that we can write a vector in component form by considering its magnitude as well as its direction. Thankfully, we already know the magnitude of both of these vectors. So for example, F, the F vector, I can write it as its magnitude of 25 miles per hour times the vector cosine of theta. This would be theta for F and sine of theta for F. I write theta of F instead of using 30 degrees because 30 degrees would not be my angle measure theta. Theta should be a standard position angle measure, not a bearing. If I want to find the standard position angle measure for F, I need to consider that to be from the positive x-axis, the counterclockwise rotation. Meaning that we are rotating 90 degrees through quadrant 1, plus an additional 30 degrees through quadrant 2 in order to end up to the vector for F. So overall, this is 120 degrees as a standard position angle measure. So F would be, if I combine this all together, 25 cosine of 120 degrees and 25 sine of 120 degrees. C, on the other hand, is going to work very similar. However, C has only a magnitude of 5 miles per hour, and it is going in a different direction. It has its own angle measure defined by c for both sine and cosine. Now we need the standard position angle for c, or the vector for the current. In my picture over there, the standard position angle would be from the positive axis, rotating counterclockwise here, towards where the vector of c lies in quadrant 3. Well, that means that we are rotating a full 180 degrees plus an additional complement of 50. This would be 40 degrees. 180 plus 40 would give us 220 degrees as a standard position angle. So that would be now 5 cosine of 220 degrees and 5 sine of 220 degrees. Now, unfortunately, I am not familiar with cosine of 220 degrees or sine of 220 degrees, so I'm not going to simplify that any further for the time being. I will at the end of this process when I get the speed and the bearing, but for now I'm going to keep those as they are. I can, though, simplify f if I so please, because we should know cosine of 120 degrees as well as sine of 120 degrees. Cosine of 120 degrees, that would give you negative 1/2, so this would be negative 25 over 2, or negative 12.5. And sine of 120 degrees, that is positive square root of 3 over 2, so that would be positive 25 square root of 3 over 2. If you choose not to do this, that is also perfectly okay. I will choose to use these values, though, simply because it takes up less room. But we can now evaluate our addition of vectors here, f plus c. That resultant would now allow us to be able to calculate this because we can add up our corresponding components. We can add the first components together, so that would be negative 25 over 2 plus 5 cosine of 220 degrees. And we can add the second components together, 25 square root of 3 over 2 plus 5 sine of 220 degrees. This would be the combination of f plus c. Now that's all well and good. We have now found a component form for the resultant. We now need to find the true speed and bearing of this based on that resultant. Well, speed was what we used for magnitude for the previous two vectors, meaning if I want to find the speed of this resultant vector, I need to find the magnitude of it. It's not going to be the prettiest thing in the world, but the magnitude of f plus c, that, using the Pythagorean theorem, would be negative 25 over 2 plus 5 cosine of 220 degrees squared plus 25 square root of 3 over 2 plus 5 sine of 220 degrees, also squared. That should all be under a square root. And that would allow us to evaluate and approximate the true speed. I do say approximate because we now will need to use a calculator for this purpose. So let's bring up a calculator here. Make sure you're in degree mode since we are going to be plugging in degree measures into sine and cosine. It'll be the square root of negative 25 over 2 plus 5 cosine of 220 degrees. That quantity is taken to the power of 2 plus the quantity 25 square root of 3. That is divided by 2, and then we add that to 5 sine of 220 degrees. And that quantity is also squared. If you have trouble typing this all into a calculator because it is relatively long, you may approximate both of these terms squared first, but try not to approximate much. Keep as many decimal places as possible so you do not throw off your results. Here we get a value of 24.63, or to one decimal place, 24.6. So that would be our answer here. 24.6 for this magnitude in miles per hour. That overall means that the current isn't doing too much to change the speed of the ferry. But let's see if it does much to change the bearing of it. Well, to find the bearing of it, we are going to first find the standard position angle measure by evaluating the direction angle for this vector. So we can evaluate the direction angle for F plus C. We can do that in a variety of ways. However, the most traditional way is to evaluate this using arctangent. Arctangent here of the second component over the first. The second component here will be 25 square root of 3 over 2 plus 5 sine of 220. And that is going to be divided by the first component, which is negative 25 over 2 plus 5 cosine of 220 degrees. Now, I know that this overall will not give us our correct answer for a couple reasons. For one, arctangent of this fraction is not going to give us a standard position angle measure in quadrant 2, because arctangent cannot do that. It can only give us an angle measure between negative pi halves and pi halves, or in degrees, negative 90 degrees and 90 degrees. In order to get to the correct angle measure in quadrant 2, we are going to need to take the results of this arctangent value, and if we add 180 degrees to that, that will give us the correct angle measure in quadrant 2. Or if this was in radians, we would be adding pi. So let's bring up a calculator here. I'm going to work through this relatively fast. Had a quick typo there where I had a multiplication, but if I put this in correctly, we get to 131 degrees, 0.5. So that would be approximately 131.5 degrees. I'm not going to box this because that is not the final answer. We need the bearing. Bearing should always be an angle measure that is either in reference to north or south, whichever one is closer. In this case, 131 degrees in quadrant 2 is closest to north, and we can find how much from north we are going to be turning west by simply subtracting 90 degrees from this. If we subtract 90 degrees from this value that we have of 131.5, that will give us 41.5 degrees. And that will help us with our bearing. Our bearing is from north, turn 41.5 degrees towards west. And that is our bearing. So overall, I would say here that the magnitude of the current, the speed of it, did less to influence the speed of the ferry as it did to influence the bearing of it, particularly when you consider that changing a small degree measure over a long period of time, like a value of miles, can do a lot more to influence where you end up. I did, however, say that I'm going to demonstrate how to do this problem in a couple of different methods. So I'm going to take some of this work away, and I'm going to restart this considering a different way of evaluating this problem. I have erased the previous work, but I did keep the two answers that we came up with, 24.6 miles per hour and north 41 degrees, or north 41.5 degrees west. I'm going to show a second way of solving this problem that to some may be a little bit more simple that we can do when working with a two-dimensional demonstration like this. We're going to get the same answers. I have also kept the picture from before because I'm going to use this picture to establish what we will be doing. Note that I am adding the vector for the ferry and the vector for the current. In this case, I have the ferry vector in red, and I have the current vector in black. And I said the resultant should be the vector that comes out in between those two, likely somewhere in quadrant 2. Another way that you can visually represent adding two vectors is by, for example, f plus c. By following the vector for f first until you get to the terminal point for f at the end of the arrow. And then from that terminal point, draw the vector for c. The vector for c from that terminal point, south 50 degrees west. When I draw that, the terminal point of that vector for c should now end up where the resultant of both f plus c is. This is another way to write an addition of vectors. Follow along the track for one vector, and then from the terminal point there, connect the next vector. Some people say from the tip of the vector to the tail of the next. But what this means is that I now have a triangle that I can work with, and I should be able to actually evaluate some of the numbers in this triangle. We have, if I redraw this triangle here, clean it up a bit, we have this small side length has a magnitude of 5, and this longer side length has a magnitude of 25. What we should be able to figure out is actually the angle measure in between these two. As if we use properties of angle measures, the ferry vector that we had originally an angle measure of 30 degrees from north, or realistically, that is 30 degrees from a vertical line to this diagonal line. Well, if I draw that vertical line through my new triangle, that vertical line to the same diagonal line should still be 30 degrees. I can also do that same concept with the bearing for the current vector I had. This bearing of 50 degrees is from a vertical line to that diagonal line. So again, from a vertical line to the diagonal line for the current is 50 degrees. Meaning that overall angle measure inside there is 80 degrees. So this angle measure here is 80 degrees. This is using concepts of what is called the vertical angle theorem. But overall, I'm basically just manipulating angle measures to get a more convenient triangle here. And this is relatively convenient because I have two side lengths of the triangle and one angle measure. That means that I should be able to use concepts of the law of cosines in order to solve, in this case, the other side length, which would be the magnitude of the resultant. So, let's use law of cosines then to solve this same problem. If I want to solve for x using the law of cosines, that would take the other two side lengths squared, 5 squared and 25 squared, and then minus 2 times those side lengths, as well as cosine of the angle measure in between. The square root of that should help me solve for the value of x. That x, since we have the other values of the side lengths as the magnitudes of the vectors, x here will also be the magnitude of the resultant, or the speed of it. So let's use a calculator for that purpose. We will have the square root of 5 squared plus 25 squared minus 2 times 5 and 25 times cosine of 80. Do make sure you're still in degree mode here. And we get, yet again, 24.6. Actually comes out exactly the same as the value that we got in the previous situation. So we still get 24.6 miles per hour. That means our speed agrees with what we got before. But now we need to get the bearing. Well, to get the bearing for the vector for the current, which I will draw in red in this triangle down here, The bearing is supposed to be from north. So I need to find the angle measure from north to this vector. Thankfully, I already know a portion of this. I know a portion of this is 30 degrees, based on what I know about the bearing for the ferry vector. So, as long as I can find the angle measure inside here of this triangle, then I can add that to 30 and get our overall bearing. Since I'm simply looking for the angle measure inside that triangle, and I now have enough information for a side length and an angle measure across, I can find out that value of theta using the law of sines. So, the way that would look, sine of theta divided by the side length across from our angle measure theta I'm trying to solve, which is 5. I'll set that equal to the ratio of sine of 80 degrees because we now know that this is across from the side length of 24.6. Or to make sure I'm a little bit more accurate here, I'll say 24.629. I can then solve for theta by multiplying 5 and taking arc sine of both sides. Theta will be arc sine of 5 times sine of 80 degrees divided by 24.629. And from my picture, I do expect a very small acute angle measure, so I don't need to worry about ambiguity here. I should be able to approximate this using a calculator and get the angle measure inside the triangle, which will allow me to find the bearing. If I do use a calculator for that purpose, that would be arc sine of, we had in this case, 5 times sine of 80 degrees, make sure you're in degree mode, divided by what we just solved for, which was 24.629. That gives me an angle measure of 11.5 to 2 decimal places, or 1 decimal place. And as I had just said, if I combine that with the bearing for the ferry, which is 30 degrees, I should overall be able to find the bearing for the resultant vector. This will be 41.5 degrees. And just as we were saying earlier when establishing the bearing, this is from north turning towards west. So yet again, we get the same solution that we did in the previous case. That is 2 different ways of demonstrating and working through this problem. Whichever one you prefer to work with is really up to you there. I do want to make a note, however, that the method that I did the second way here with law of cosines and sines, that will only work if you have a diagram that is in 2 dimensions. The reason that the other method tends to be used is because if you were to go beyond this with diagrams and vectors in higher dimensions, like a 3-dimensional diagram, then those concepts will not apply in the same way. So it is better to have that understanding of how you can create the vectors in component form and combine appropriately.